let's go ahead here and take a look for a few minutes at dynamic routing protocols. This is going to be, I expect, one of those days to where we're going to have a considerable amount of lab time available, because this is one of those things that, you know, we rush, and all of a sudden we get towards the end and we got all this kind of extra time, kind of not extra time, but kind of extra time. But dynamic routing, and we've talked about static routing. You looked at that. Static routing, the big deal with static routing is you got to get there and you got to get back. I had a student, and this was a couple years ago, went in and said, okay, I've got this project. He after he finished these courses, he went into a bachelor's or master's degree, and they were setting up a network. He said, I can get to the ISP with my static route, but I can't get back. You got to get back also. That's one of the multiple disadvantages of static routes. Is one, it's easy to make typos. Two, you got to get there and you got to get back for every single destination that's en route. So the big advantage is they don't get shared unless we do something like anyway, when we sent the default gateway, default information originate, that would send the default gateway. You can put the static routes into a dynamic route and they'll be propagated. But other than that, the security aspect is there, and it doesn't take any resources in order to have static routes. But you gotta update them continuously. Would be one of the deals if things continued to change from one to the other. So the dynamic routing protocols, unique characteristics, the differences in the dynamic routing protocols, three types, including BGP. BGP is this path vector thing. So we have a couple of different interior gateway protocol types that we're going to have: distance vector and link state. Distance vector is what RIP is, and it's the distance away, the number of hops, and the vector, the direction that it goes out of to go from one to the other. So the kind of different types that we would have from one to the other. So the dynamic routing protocols, 4 basic functions are available to them, or 4 basic functions to go on. What the basic functions are to kind of take the load off of us, to be able to dynamically or automatically share or update any route changes. So the first thing they're going to do is learn from the neighbor routers the routing information for the subnets. Remember, the first thing that a router knows, the only thing that a router knows initially, is the networks or the interfaces that are attached to it, the addresses and the networks that are associated with those interfaces. So, yep, that's what I know. Now let me tell my neighbors. There was years ago, and probably before any of you guys, there was a TV commercial for a hairspray, and it was, if you tell a friend who tells a friend who tells a friend who tells a friend, pretty soon everybody's going to know about it. And that's kind of what we're doing with dynamic routing protocols. A router tells a neighbor who tells a neighbor who tells a neighbor, and each neighbor that forwards the information is going to have some cost or some metric addition as we go down the line. In RIP, it's really easy to see its hop count, how many routers are away. In OSPF, it's kind of easy to see because we're going to have the speeds of each of the interfaces that's going to be associated with it, and we can add the cost up for that. EIGRP, the most complex of the calculations, is going to be the lowest bandwidth. I said bandwidth and delay, the lowest bandwidth, and then the summation of the delays that are available. So the neighboring routers, they learn from the neighboring routers, tells a friend who tells a friend who tells a friend, advertise to the other routers the routing information for the routes known to the current router. The routes known to the current router a friend tells me something, and then I know about my stuff, and now I know what my buddy told me, so I'm going to send all that information to my other buddy to allow those things to happen from one to the other. Identify the best route according to the advertised metric. What's going to be the best way to get there? We do that with the GPSs, and again, GPS, as I understand, actually uses the Dijkstra algorithm to calculate the shortest path. You usually get 3, or I get 3, and I'm sure everybody does. That's what they all do. You can pick the best path, the fastest path, or the alternate path, whatever that one might happen to be. If the topology changes, and here's the big deal, the link fails or something like that, that reacts by advertising that some routes have failed, and pick a new currently best route, if there's one available. I mean, it may be a situation that there isn't an alternative when we do these things. Hundreds of routers, a dynamic routing protocol is practical. I think even in just a very few routers, a routing protocol is the thing that we're going to want to use. It's going to be the practical element that we want to do. Stable network is one of the other characteristics that we want for static routes. The ever-changing routes, if you've got things that are changing consistently, persistently in your network, you're going to want a dynamic routing protocol. Interior gateway protocols are the ones that are used in the local area network. So this one says IGP. IGP is a really old protocol. I think this is the one that went away somewhere around 1992. It was replaced by EIGRP. Actually, my brain went the wrong way. Interior Gateway Protocol, IGP, because there was one that was called IGP, Interior Gateway Protocol, and then Enhanced Interior Gateway Protocol. IGP, Interior Gateway Protocols, are the ones that we use within the enterprise. IGP was an old protocol. Several of them here. We have EIGRP, Enhanced Interior Gateway Routing Protocol. So several of them. OSPF is the one that you want to focus on. Know a little bit about these others, EIGRP and RIP v2. RIP Next Generation is for IPv6. None of the routing protocols for IPv6, at least for me, weren't tested. No guarantees, obviously, and we'll look at them very briefly just to see the differences. And the way that you implement IPv6 is a little different, a lot different than you do for IPv4. Maybe simpler, maybe more complex, but it's just different when we do those things. So the IGP, routing protocol used for exchanging route table information between two of your internal routers to do these things. To know the difference between an interior and an exterior gateway protocols. Exterior gateway protocol is BGP, and it's called a path vector protocol. The interior gateway protocols, RIP v2. RIP, there are actually two versions. RIP v1 is a classful protocol. RIP v2, classless protocol that we have with it. And then we have EIGRP. I'm going to say Cisco proprietary. Cisco opened up some elements of it several years ago, but nobody's doing that as far as I can tell. Nobody's using it because I think they're afraid that, hey, if we do this, then Cisco's going to come back and ask us for a royalty to use the elements of it. They didn't open up the whole protocol, just part of it. So I'm still going to call it a proprietary protocol. It works really well with Cisco in an all Cisco environment. The different protocols here, we have the protocols, the link state, the advanced vector, the algorithm, Bellman-Ford here. What we don't have, we do down here at the bottom, kind of inversely here, the protocol, RIP v1 and RIP v2, Bellman-Ford, it uses hop count. EIGRP, which is, again, the Cisco proprietary, is called an advanced distance vector. Some people call it a hybrid protocol. Cisco likes to call it a hybrid protocol. It's going to display characteristics of both a link state, the next one, as well as a distance vector protocol. It's got a hop count, but it's a huge hop count. It's really not used. One of the differences is over here, the distance vector protocols update every I want to say 60 seconds, 30 seconds. We'll get the time when we get there. So Bellman for diffusing update algorithm dual, and one of the ways to remember this is EIGRP. The letter designation is D for it for whatever reason, but D dual is the algorithm, diffusing update algorithm. It uses bandwidth and delay. There are actually 5 characteristics that can be used, but only 2 of them are in use today. So you may see that they're called K values. There are 5 K values, 2 of them are used when we do that. Link state is the one we're probably going to focus on, and we'll do link state tomorrow with the Dijkstra algorithm, the SPF, the shortest path first that goes along here. It uses cost, and cost is associated with the bandwidth of the interface. OSPF is the one that we're concerned with. IS to IS, intermediate system to intermediate system, is also a true link state protocol. So kind of an overview of interior gateway protocols. Distance vector is going to be RIP. Probably one of the easiest ways to do that is to look at a RIP here, and I got the wrong one open, of course. And one other thing while we're doing RIP is a couple of other things. Auto summary and no auto summary. What does auto summary mean when we do that? So in a RIP environment, we have the hop count. And if we go into this thing, we've got to give it a few seconds, because spanning tree here is still doing its thing on our switches, checking to see, even though these guys are not going to cause loops, even though that's happening. I didn't do port fast on them, so they're still going to go through the entire process. Let's see where we are in the entire process here in the show spanning tree. So we said, okay, good, they're all turned green, they're all in forwarding state. If I go into this router and use a show IP route, obviously, let's spread this out a little bit. Show IP route. Then we're not there yet. So show IP protocols, and it says that RIP show IP protocols is a command that you can use to see if the protocols that you think are running, and it says is RIP, updates every 30 seconds, next due in 1 second. So next due in 1 second, maybe we've got some show IP route here, and we've got some RIP routes starting to come into this thing. We've got a bunch of RIP routes coming into it. So to get to 192.168.3 network, we have the administrative distance of 120, which is the highest, 90, 110, 120, and 115, I think, was IS to IS. So the kind of who is what when. Yeah, everybody's having issues, Travis, because the thing is down, and that's why I'm waiting. They've given me an address to do. I'm waiting until we give everybody a big chance. They said they're going to send a link out for everybody to get in. I don't know if anybody's got it or not, but if you have the email address of any of the other students, good morning. Please let them know. Yeah, I know everybody's having problems this morning, Stephen. Okay, now we're getting there.
That's crazy. I had to message the ACI learning thing, and they gave me a link.
Good. We're getting there slowly but surely, it looks like. And what Travis asked, no, I have not done attendance. I can't do attendance. I can't put it in because it's down for me just like it is for you. but they gave me a link, and I'm waiting. I'm going to wait as long as I can until to give everybody a chance to get here. Let me try this thing one more time and see if it is still down, and it is. So anyhow, hopefully that helps. It's not anybody's fault that you're late this morning. I'm just glad that you could get here. Yeah, good thing. Yeah, Zoom, but it's had its issues too, Travis. It's gone down in the past, not while I've been doing a class, but I have seen reports that, oh, Zoom's down or this is down. A lot of these guys use, or all of them use, the cloud, and when a cloud provider has issues, they're going to have issues too, and that may be what's happening with a Docebo. I don't think that they actually have a physical server that they run, but they may when we do those things. But again, still waiting here. We got 3 to go, and yeah, 3 to go. Hopefully they'll be here, and then I can send, maybe at the break, send the attendance for those things. And I told her that I was going to wait as long as possible. I'm going to wait, give everybody a fair chance to get here, since not your fault. Anyhow, back to this. The administrative distance you can see here is 120, and if we can find this 192.168.3 network over here from router 0 that I'm on, it says the metric here is 1, which says it's 1 hop away. So the 1 hop would be, we get into here and we go across this router. Switch doesn't count, obviously. We'll go across this router to get to this network. So that's going to be the 1 hop that goes along with RIP. The way that these devices find the outgoing interface, because again in the route table we've got the destination network. This one's directly connected. It's a C. And the age of the network, you notice this one doesn't have any L's. The old networks didn't have L's. They had C's, so it knows the interface that it's connected to, or the protocol does. So where were we going? To the 3 network here. 120, the administrative distance, which means of the dynamic routing protocols that we use, it's going to be the least trusted. 1 hop away via 192.168.100.1 should be this interface, the next hop IP address that goes along with it, and then kind of wraps around, goes out fast Ethernet 01. The outgoing interface is determined by which interface the routing information comes in on. So the whole sharing process is one of those things that's going to go on from one to the other to allow these things to happen. So it will then, it gets the information about the networks, and the networks on the individual interfaces. The individual interfaces have to be advertised, even if there's not. This one back here will go to up to this one here. Just a second, let me get rid of all this mess here. This one has a network attached to it, an additional network attached to it, in addition to the interfaces that are available on it. So if I go into it and use the, let's just use on the a show run command, the way that we tell the system to, hey, RIP is your protocol and here are the networks. So router RIP, and you have to specify version 2. If you don't, then you get a version 1 that goes along with it. So I'm advertising network 10.0.0.0, 172.16.0.0, 192.168.3, 192.168.100. I've got some loop backs on this thing, the 10.4.4.1, in order to give it something to advertise, and that's why it has more, but from one to the other. The interface is gig 01, the 100 address, and gig 00, the 3.1 address. We have to advertise those 2 networks to activate the protocol on the interface. Activate the protocol on the interface allows it to then go in and exchange information from one to the other. Say, let's debug. Let's look at debug IP RIP. This one's an easy one to see every 30 seconds, so it'll just take not too long for it to start sharing the routing information, unless I just missed a time, then we'll have to wait the full 30 seconds. Here we go. So it is then, and one of the ways to get rid of the debug is no debug, undebug, or just you all. Undebug all turns off all the debugging. Undebug is the only thing that starts. That's the one command that is different from the no. You can still do a no debug, but you can also use the undebug command in order to do that. So these guys are sending information, received update from 192.168.100.2 on gig 01. So it now knows that 172.16 is one hop away. 192.168 is known down the line. The way that it knows the next hop IP address and the outgoing interface is this where it came into. It came from this address. Hey, that's going to be, if they're the one that sent it to me, that's the next hop. And this is the interface it came in on, so that's got to be the outgoing interface to get to that particular device. Just what does a RIP, and this is the simplest of the routing protocols, and it's easiest one to see, I think, kind of what goes on in the transmissions. If you want to see what's being sent from one to the other, debug is the way to go with these things. So we have that capability. One of the things that I do want to do or talk about here is auto summarization, which is inherent in some protocols and not in others. It's inherent, part of the default of RIP v2. It can be turned off in RIP v2, and these are RIP v2, RIP version 2, so it can be turned off. What auto summary does is automatically summarizes at the classful boundary for things. So in this case here, I want to go from this guy to the 10.10.10.1 address, because I've got 10 addresses on a number of these routers. If I ping 10.10.10.1 for this thing, and it's got to go do the ARP and all those other things. So now we're finally getting there. But you notice that, I'm going to go get a full one here. You notice that we get an exclamation of success, a dot of failure, an exclamation of success, and a dot of failure. Reason is that if I go to the show IP route command for the 10 network, it's only got one entry, because auto summary, which is the default for RIP v2, or for RIP anyway, RIP v1, you can't use the no auto summary. So it sends one of them up here, and then it sends one of them over here, a bunch of 10 networks over here, and then one up here and one over here. So it gets a little bit confused. The no auto summary, where we tell it to use subnetting, is going to be, should be, a different situation that we have here. So we can go in here and ping 10.10.10.1, and we got to go through the ARP resolution and all those other things. And this one got two. It is typical in the Cisco world for the first one to fail. And this one, we got the first two fail because ARP is still resolving. The ARP protocol is still resolving the MAC addresses for these things. So we had 100% success going to our individual device. So to show IP route here, if we look at the 10 network up here at the top, and this maybe we have the network here, variably subnetted. So we have the more specific, or we have the more specific, the less specific. So we have the 10. But when it's going to the 10.10.10, it's looking for the longest prefix. Longest prefix, most ones in the subnet mask, the biggest number in the / that goes along with these things. So we have, going to the 10.4.4 network and the 10.10.10 network, we have a longer prefix, a more specific route to go to. It's going to use those routes. For all of the other 10 addresses, the ones that are out there hanging out on that other router by themselves here, which I didn't designate here, it's going to use this route in order to get to them. So the longest prefix, they go somewhere addresses, and then the network addresses are kinda, I think, hopefully demonstrated here a little bit. So with that, maybe now can go a little faster with these, huh? Distance vector algorithm that goes along with it. RIP is a distance vector, 2 versions, version 1, version 2. Version 1 is really old. Version 1 is a classful protocol based on the distance and the vector. The distance is how many hops away. The vector, the outgoing interface that goes along with it, that goes with it from one to the other. So we're still building. That's good. No, that's Will again. So when we do these things, each router only knows the routes that are direct neighbors. This is sometimes called routing by rumor. A friend who tells a friend who tells a friend who tells a friend, and the others we say, well, they don't really do that, but they really kind of sort of do that. The issue with RIP is that it only uses hop count. So if we had a situation, an odd router up there, like this, where we connected these guys all together. We got 2 paths from source to the destination, from the one on the left to the one on the right over here. And we go in here, and this was, and we'll make it something really bad, 56K. And this is a 56K. And this is a 1 terabyte, and this is a 1 terabyte, and a 1 terabyte. It's going to pick the 56K because of the hop count. There is 1 hop here, and there's 1, 2. Actually, going to this network, we would have 1, 2. We would have 2 hops here. Going in this direction, we would have 1, 2, 1, 2, and then 3 to get there. Since it's a greater hop, regardless of the speed, it's going to take the shortest distance that is part of, or that is the protocol, which is going to be that, hey, I'm going to go the 1 hop away for these things. RIP and EIGRP. EIGRP, and it says our distance vector. It's a distance vector protocol at heart, and if you ever see that at heart, but we normally, or at least in the Cisco world, are going to say, hey, it's an advanced distance vector, or it's a hybrid protocol. The routing protocols, EIGRP sounds some qualities of the link state, so down here it's a hybrid protocol. It's got a big hop count, and when we look at it, we'll see see some of the specifics about it. Only the number of routers that are passed and what it was trying to do there, whatever we would do from one to the other, getting from point A to point B, RIP only considers hop count. Link state is a different animal. Link state here is a form of routing where the various devices that perform packet forwarding outline all of the connections that are available internally to allow the quickest convergence. What does that mean? And we'll talk more about that tomorrow with OSPF, because OSPF is the link state protocol that we use. So what it does is defines the link, and the link's the interface. Up, down, IP address, speed. The big thing is speed, and the speed's going to be, the speed is going to have a cost associated with it, with a cost table, and we talked about the default, the basis is 100 megabits per second, configurable so that we can account for the faster ones, and again, that's the kind of a thing for tomorrow. But the link state protocols, OSPF, share all of the information, the topology information within the network, and we'll see how we'll figure out what the network is when we do the configuration. It's going to be called area, that they'll all share the information with. So once they have done that, each of them has a topological map of the entire network. From that topology table, that topological map that they've created, they're then going to go and calculate using the Dijkstra algorithm the shortest path, the SPF shortest path first, in order to get from one to the other. So it's going to be significantly faster than what goes on. And I think that we've probably, hopefully, done this already. Is a distance vector internal routing protocol suitable for small networks. Suitable for small networks because a hop count of 16 is going to be infinity. So it has a limited hop count that can be used for it. 0 to 15, if you see a hop count of 16, it ain't going to work no more for that one. It says it's still one of the most widely used protocols. It's really easy to configure router RIP and then the network. You don't, nothing that goes on. Hop count is the thing that's going to be used. And this one here, it's going to go directly here, even though it's a 256K versus the what would wind up being 100 meg if we went back to these things, but much faster in this direction. But the single hop going from this to the other is what would be calculated in this one. Easy to set up. Small networks uses hop count as the metric, updates every 30 seconds, and you saw what the update looks like. What does a information sharing of a RIP route look like with these things? RIP has a number of timers that go along with it, and I think that I got my timer in here too early. Let me get it out of the way, and then I'll bring it back in a second. But the RIP, a distance vector classical protocol, 4 basic components. The routing update process happens every 30 seconds. The RIP metrics, the hop count, and the routing stability. Routing timers go along with this, and it's easy. Benefits easy to use. Compatibility with diverse devices. It's been compatible with Windows routers for a number of years. I think OSPF is compatible now, but RIP, you could go in and configure a Windows server as a router, and it would use RIP in order to go there. RIP v1 is class full, which means it cannot be subnetted. RIP v2 can be subnetted. RIP v2 is okay for variable length subnet mask, any kind of subnet mask that you want to use, as are the other 2 interior gateway routing protocols. Well, we'll say the other 3 if we throw IS in there. Hop count greater than 16. Infinity prevents routing loops. 0 to 15 is where we get the 16 again here. Suited only for small networks. So small networks is what we would have for this thing. Split horizon, route poisoning, hold down. The number of timers, and that's what this is here. Let's see if we can get this in where it maybe is visible. I got too much stuff on this thing now. The hold down timer, the route flush timer, the update timers every 30 seconds. Nothing happened, 180 seconds, the route invalid timer. So we're now going to say that this route is invalid. After that, it's going to flush the route out of it, 240 seconds. And then the hold down timer says, I'm not going to take anything better here for a little bit longer. So it then waits a little bit longer in order to get from one to the other to do these things. So the timers, and these are not anything you're going to need to know. You just need to know that, yeah, it's got timers. And the timers allow for the updating that's going to happen with these things. Look like maybe the email finally got there. For those of you just getting here, I'm recording this, and I'll post it after we get done if you want to go watch it. And I'm waiting for, actually, AJ said that he had a tree fall. His power was out. I'll go ahead and tell them that everybody's here except him at the break when we do this, because I can't update. It's down for me too. I can't update attendance. So you haven't missed anything. You're going to get full credit for being here today for this. So the RIP simple protocol, easy to install. it's one autonomous system. The routers are going to be RIP speaking devices, and then another autonomous system. Autonomous system is again going to have like 3 different meanings. Autonomous system we've talked about under a single administrative control. Your network, wherever you're doing your network, autonomous system. BGP, IANA assigns autonomous systems. They're going to be related with the big ISPs, the big ISPs of the world. And then EIGRP, we're going to assign our own autonomous system to them. And in the EIGRP autonomous systems, only the devices that are in the same autonomous system are going to talk to each other when we use those. RIP v2 and RIP next generation. RIP v2, 1993. Authentication, key management, route summarization, site, or VLSM. So Route v2 is a non-classful protocol. RIP v1 is classful, doesn't care anything about subnetting to get from one to the other. So RIP v2 will take into account all these other things: authentication, key management of the authentication keys that go along with it. Route summarization, saw a little bit earlier, we can turn it off. The default for RIP v2 is route summarization. Route summarization summarizes the route at a classful boundary. So if I had a 10 network, it thinks that all of the 10s are here. If I have a 172.16, it's going to think that all the 172.16s are here. The 17s and on down the line. So the classful summarization happens by default on RIP v2. It is one of those that can be turned off. No route summary is the command that we would use for it. Automatic route summarization by default, no auto summary to turn it off. Uses a multicast address. RIP v2 is multicast, as is OSPF and EIGRP. Both of those use multicast addresses for the routing protocols to share the route information. RIP v1 is a broadcast protocol. So multicast versus broadcast, v1, v2. Subnetted, not subnetted, v1 versus v2 versus v1. v2 subnetted, v1 not. v1 versus v2, no subnetting, subnetting. Auto summary, auto summary, v1, v2, auto summary. Auto summary can be turned off if we want to. So in the commands here, the version 1, and this is one that if you get into a network that probably you didn't configure and somebody didn't state the version numbers, version 1 enables RIP v1 only. If you don't specify a version, then you send v1 updates, but listen for both v1 and v2 updates. And that's the one that can get kind of confusing, is that I'm getting updates from some of these devices, but some of these devices aren't updating. So you may have some systems that have version 2 or configuration or no version, and you were going to it will send the v1 updates, and it's going to accept updates from both v1 and v2 devices. v2 is only going to accept or communicate in RIP version 2. RIP version 2, again, multicast address. RIP NG, next generation, introduced in 1997. It's the one that supports IPv6. Still has the 16 hop limit. Administrative distance is still 120 that goes along with it. Supports IPv6 addresses and prefixes. Uses the multicast address FF02. FF02, if you recall from IPv6, is the multicast designation, FF02::9. Notice that the host address is 9 for both of them. And for all these protocols, that's the kind of the one upside that they did for us, that the multicast 224.0.0.5 or .6 or .9 or .10, FF02::5 or 6 or 9 or A for 10 that we would use for each of those. No advertising of the network's IPv6 unicast routing, and this is for IPv6. no advertising of networks will look at when we look at some of the others. They all work the same. When we looked at the RIP, the router RIP, and then looked at the network statements, we advertise networks. In IPv6, you put the protocol on the interface. A little bit different configuration information that goes along with it. I want to try to finish RIP here. We should be able to. There's only a couple of slides before we take the break, and then we'll take a break here. RIP v1 and RIP v2, the message formats. V1, command version, the family network addresses, and the distance fields. The big deal here is it is class full, where RIP v2 is classless. So in the message, the subnet mask is going to be part of it in the next hop IP address. In this one, the format consists of the command, the version, the family, network address, and the distance fields. Doesn't have a subnet mask. It is not subnettable. It's broadcast every 30 seconds, and this one's multicast. It's still every 30 seconds, but it is a multicast instead of a broadcast, which quite honestly doesn't really make that much difference, because when we talked about these things, what's flooded out, traffic is flooded out all of the ports. It's going to be broadcast traffic all the time, broadcast traffic, unknown unicast, and multicast traffic, unless you configure the switch to say, hey, don't send the multicast traffic out of these ports, which you can do, but that's something that's beyond CCNA. So RIP here will aid in understanding the setup of initial network. It is an absolutely easy protocol to configure, router RIP, and then whatever the network address is. You notice that even in the the RIP version 2, we didn't use the subnet mask, or actually in routing protocols, we're going to use wildcard masks to designate. Wildcard masks are just the inverse of subnet masks, and we'll look at those when we get there. So as RIP can only pass over a maximum of 15 hops, greater than or equal to 16 becomes infinity, from their internet-facing router to the end user, could use this protocol to route traffic. Small networks that can be used. It can be used on small networks. 0 to 15, 16 hops is the maximum that is allowable in here. The next protocol that we're going to look at is EIGRP. So the next interior gateway protocol, EIGRP, there was an original one. This is enhanced. The original Internet Gateway Routing Protocol was Cisco proprietary, went away somewhere around 1994. So when we talk about these protocols, and when we talk about CCNA and what's new and what's not new, much of it has been the same for a very long time. Configuring OSPF for version 4, still the same. It was, what, 1998 or something like that. 97 was it. This one, about 94, 95, been configured the same way. RIP's been configured the same way. So when we get into the tests and what's different and what's not different, a lot of it is not different. It's been there forever and ever and ever. The way they ask the questions is what's new, and that's, for me, the practice for the practice questions, as many practice questions as I can have here. So EIGRP, the Enhanced Interior Gateway Protocol, Advanced Distance Vector is the term that goes along with it. So Advanced Distance Vector, EIGRP here, public use is an Advanced Distance Vector. Cisco did release for public use as an informational RFC, but I don't think anybody's using it, because I think the fear would always be that, okay, yep, they said we can use it, now let's embed it into our operating system, our iOS, and then all of a sudden Cisco says, well, we want a royalty because it's ours. So it is, and it's still mostly considered a a proprietary protocol. Several metrics and supports multiple paths for it. EIGRP, better, more efficient, upgrade to RIP, was created to support classless addressing and was upgraded to IPv6. What I think that I want to do, and maybe it's not a good way to do it, but we'll try it out here, is go to a little topology here. This has got, part of it at least, has got both IPv4 and IPv6 configured on it. I'm going to go to this one here. I knocked Bob off earlier this morning because this was what wasn't working. So in this thing, you can see the exchanges, the interface gig 00 change state to op 0000001 on interface change state to op. Then they're going to form adjacencies, adjacent neighbors. And once they form the adjacencies, that's when they start sharing the information that they know about. Tells a friend who tells a friend who tells a friend. Maybe topology information in OSPF, maybe route information. And that's one of the differences between these that are, quote, distance vector and this one, again, an advanced distance vector. But between those and the link state protocols. The link state protocols share the state of the links. They share the link information. They don't share routes. So there is no such thing as a route summary or a no route summary in those. This protocol is again, at its heart, is going to be considered I'll try to get this in the middle and spread it out. Is considered at its heart a distance vector protocol, but advanced distance vector or hybrid are probably the terms. If we do a show IP protocols here, the protocols that are running on it, we have the routing protocol is EIGRP. 20 is its autonomous system number, which means that it's going to share information with all of the other routers that are configured as EIGRP20, that are configured in this autonomous system number. It's significant in our network only, and what it does is say, okay, all you other guys share that are in this autonomous system, share your route tables with everybody else that's here, so we can create a network that we know where everything is, and then no filter lists. The default networks flagged in outgoing interfaces. The default networks are accepted from incoming interfaces, default networks that could be available for these things. It says redistributing for EIGRP20. That means it's sending that information. Redistribution is a process that we could use to maybe, if we had down here, let me just, so that I can get some areas here. If we had down here, we had a RIP network, and we had RIP and EIGRP running on this network. We could redistribute the RIP networks into EIGRP, and it would advertise them. It would come back to this device, and then it would send them using the RIP protocol to the RIP network. So this is redistributing or sending updates for the redistributing for EIGRP20 for this autonomous system that we have for this. Got it, Ashton. Take care. Good luck. So we have that redistribution that goes along. If we had multiple autonomous systems, we'd have to manually redistribute one into the other in order to make these work. So EIGRP IPv4 protocol for autonomous system 20. The metric weight, you notice here we have a K1 is 1, K2 is 0, K3 is 1, K4 is 0, K5 is 0. So there actually are 5 metrics that can be used in EIGRP. Only 2 of them are. This is not the metric. This is the multiplier for the metric. So whatever, and bandwidth and delay is what these are. So bandwidth is going to be the metric is multiplied by 1. We could change that configurable, a configurable value that can be aware of these things. The The hold timer here, 240 seconds. Hold timer, how long are we going to have to wait until we consider a network down? The router ID, and the router ID becomes a kind of a significant thing. The router ID, think of the name of the router. This is another one of those that you probably want to use a loopback interface to be able to do the router ID for these things. So they're going to be automatically calculated when we do this thing based on the highest IP address, I think is what would be on this particular one. I'll have to look and see if it in fact is, or if we can use the router ID command in order to specify it should we want to do that. Maximum paths here is 4. These are for equal cost sharing maximal paths. So if we have a bunch of routes that all have the same metric, then we can have up to 4 of them by default. And again, another configurable, and I think configurable up to somewhere around 8 for these things. The distance, I skipped over distance here, not on purpose, but the distance here, we have 2 of them for internal and external. The internal, all on the same autonomous system. The external came from someplace else to do these things. So the external not nearly as trusted as the internals, where they directly share the information for these things. But this is the distance here is the administrative distance for the internal and the external. So if we redistributed something else in here, we get into some external routes that were available on it. And I don't think I have any in here to do that. So the maximum paths, equal cost paths, the maximum by default is 4. The maximum hop count here, 100. It does have a hop count, typically not going to be used for these things. Variance is something that is unique to EIGRP. What variance allows us to do is to have unequal cost paths. So that if we had, for instance, up here, and I don't really have any good unequal, well, we do. If we're going from this network up here, the corp down here, to router 0, then we've got a couple of paths that go along with it. We could assign a variance to one path or another path. What this would typically be is we would go to the same next hop for each of these things and allow it to use those things. So if you had one that was twice as good as the other one would get two and the 2 packets, and the next one would get 1 packet, and on down the line like that. So instead of having to have equal cost paths, and all 3 of the interior protocols that we are concerned with have equal cost paths available to them. EIGRP is the only one that has an unequal cost. Automatic summarization, and it's disabled. No auto summary is the default for this version of, and this is one of those that you're going to see in some of the books that says, okay, yeah, it's enabled by default. It's not enabled by default. It depends upon the version that you have. So this particular one, no auto summary for this thing. Automatic summarization here, maximum paths are 4. The maximum paths here is, again, equal cost. Routing for networks. These are the networks that are advertised. We saw, and we'll look at how we advertise them here in just a second. We saw how it worked in RIP, which was just RIP, router RIP, and then then the networks that we're going to advertise. We're going to have a little bit more detail in some cases, many cases, for the other protocols. There are cases where I want to just advertise everything that's on it, so you can just say the 0 network, so we can advertise everything that's on this thing. Passive interfaces here, gig 00. Passive interfaces say, I don't really want to play in the game, so gig 00, and I think it's one of these up here, gig 00. There is no router out here on this interface. There's no need for it to be accepting or sending EIGRP information. So we just turn off EIGRP on this one to keep it from sending the traffic back on the interface. So this network can still be advertised in the scheme of things, so that all the other routers know how to get to this IPv4 network, or in this case IPv6 network. I don't have the IPv4 ones showing here, but they still get advertised, and we'll look at that here in just a second. So passive interface, no need to send extraneous traffic out here for any reason, so we just want to do that. So it's routing, sending information about all of these, and you notice I've got the 10 network as well as the 10.0 network. It just for the heck of it, I think is why I did that. Routing information sources, the gateways where the information comes from here, and the distance 90 again is the administrative distance, and the last update, how long ago was the last update for these things. A number of characteristics about EIGRP. I'll show IP, EIGRP into the question mark, interfaces, neighbors, topology, and traffic. So let's just do interfaces. EIGRP interfaces here. Not really a tremendous amount of information on these things. So interfaces here, EIGRP interfaces for process 20, autonomous system 20 here. These are the interfaces that are involved in exchanging traffic for these things. Gig 01, peer 0, and you saw up here where the gig 01 was the one down here that had the switch on it and the PC. So it has no peers that goes along with it. The round trip time here, the mean system round trip time that goes from 1 to the 0. Pacing time and then over reliable, the reliability is 10 here. Some characteristics that go along with it, and it says, hey, these other guys have one peer. They're connected to one other device. We have a couple of serials in here and a gig port that are connected to other devices, so those are going to be the peers. When we get into OSPF, the show IP OSPF interfaces is going to have a much more information. So IP EIGRP, and we'll go let's look at the neighbors right here. The neighbors here, the numbers over here, just the order that they were that they went into the table with. Hold up time here, 14 seconds, 12 seconds, and if we do a show again here, and I got in too fast, and you can see a countdown to 5 from 15 to 10, and then it will be reset to do these things. So how long is it going to be there? At the uptime here, we're going to have 20 minutes for each of these things, and something like that. And this is going to be the round trip time from one to the other. The address here is going to be what it's going to be known as. This is going to be the host name that's associated with these things. No, it's not either. That's going to be the address of the interfaces that we have for them. So the 172.16.10.6, 172.16.10.2, different capabilities, the neighbors, the directly connected devices that we have for these things. And if we do let's do a show IP interface brief just quickly here. So we have the 16.10.1 and .5. These devices, these interfaces here, the 1 and the 5, and if we go back here, 16.10.172.16.10.6, these have got a 30-bit mask on them. That's why we can use both of these. So the serial 000, 11.2, the address, the EIGRP neighbors, the address of the neighbor that goes. That's why I wanted to look at the interfaces that we have for these things. So the usable addresses here, 5 and 6, 1 and 2 that we have for each of them. And the other interfaces here, gig 02 gig 02, 11.1, 11.2 is going to be the neighbor address that we would have with these things. The big thing, let's see, what we want, topology table. The big thing here is a topology table. The topology table, we have a couple of things in here. FD is feasible distance. And then we're going to have successors. And then we're going to have feasible successors. Different terminology. And again, since it's not a big part of CCNA, no need to get too excited, I guess, about those particular things. But the big deal about EIGRP is we have this one here. We've got two different paths listed here, via the 11.2 and via the 10.6. And it says it has one successor. And when you see successor, think successful. And it says the feasible distance is 3328. And that's related here to the, try to draw some lines here, related to the topology table. The 3328 is the total here. The first number is going to be called the advertised distance or the reported distance. This is what the neighbor said that its metric is to get to the destination. So it reports that. And then the router combines the metric to get from it to the next hop address, and mecombine those two together, and we get the feasible distance. So reported distance, what the neighbor metric is, and the feasible distance, what ours is. This one here, we start out with a reported distance is much better, and then with a feasible distance becomes a crazy number before we're going to get a serial connector in here. Is why serial 001 is why it goes so crazy. We'll look at, there's a slide to kind of go through the why these numbers get so outrageous. So we have the feasible distance, and this is the one that's going to be put into the route table, the best one, the successor route. One successor. Feasible distance is going to be the metric that will go into the route table with it. This other one just sitting here waiting. If the successor route fails, this is a feasible successor, and it'll automatically go into the route table. No recalculation required, like we would have to do with OSPF, because it's got the topology table. It doesn't have any backup routes stored. It can calculate the backup routes, but no backup routes are going to be stored with it. So here again, one successor that goes on. The feasible distance here is 3072 on down the line. There are, not in this one, I'll have to get in the other one, there are situations where we would have equal cost routes. And remember, we can have up to 4 of those. Each of these has one successor. If I go to this guy, I think that it's going to have the capability for the multiples here. Show IP EIGRP topology table down here. It's got 2 successors. So it's got equal cost or crazy cost. I did that, and they're crazy big costs, but it's got the same feasible distance for these. The feasible distance 2170112, 2,170,112. It's a number. It's a number for comparison from one to the other. So don't try to say, oh yeah, this is in megabits per second. This is what it uses is the bandwidth of the slowest link in the routed path, along with the summation of all of the delays that go in it. So, and then in this one, we'll go back to it here, and we'll do a show IP route. So when we look in it, we have all these D's here for EIGRP. This particular routers have the L's and the C's that go along with it. The directly connected, and then the L, the link, is the interface to get, the L is the link, the interface, the IP address to get to the C is really what we have with these things. So the EIGRP, D for EIGRP, variably subnetted, 8 subnets and 2 masks. The 10 network, we have the C's and the L's. I subnetted it 2432, so it really only has 1, 2, 3, 4. It does have that, doesn't it? 4, 5, 6, 1, 2, 3, 4, 5, 6 directly connected or routes that are usually not directly connected, but we have the ones that come in from the other devices too. Again, the administrative distance and then the metric that goes along with it. Big metrics, you can just about count on serial interfaces. Small metrics, you can look over here, gigabit interfaces. So the what goes on with each of those, and I think we've seen each of those. The traffic, the neighbors we looked at, the interfaces, the topology. Traffic really doesn't tell me a whole lot that goes along here. Hello sent and received, updates sent and received, query sent and received, acknowledges sent and received. So I think that we have for each of these things, and zero drops. So it gives you a kind of a quick look as to what your reliability is in that particular network. What I didn't do, let me go in here and do a show run, or try to do a show run, so that you can see how this is configured. Show run, and we will be able to see both IPv6 and IPv4. IPv6, the IPv6 address, EIGRP, the autonomous system number that goes along with it. This says, hey, participate in EIGRP. So instead of using a network statement, which we will for IPv4 down at the bottom of this, you configure the protocol on the interface. Nothing really dramatic. To me, it's a little bit of a pain, but you can quickly see where you have it configured or where you don't have it configured for these things. So we have the IP address here. This one has both an IPv4 and an IPv6. You can have both protocols running, IPv6, EIGRP 10 that goes along with this one. Down here for IPv4 router, not IPv6 router, but router EIGRP 20 is the autonomous system for IPv4. I did a variance in here I was trying to make it do something that it didn't do. And then we have the network, the 10.10.10. Instead of using the subnet mask, we use what's called the wildcard mask. So the wildcard mask 0 this would be the subnet mask would be 255.255.255.0. If you subtract the subnet mask from 255, all 255s, 255.255.255.255, be sure I got them. Subtract those, then you get the 0.0.0 to 255. What the wildcard mask says to do in this is, when you're sending something or trying to look at, should I recognize this address or not, then hey, I want to be sure that the first bit is 10, or the first octet is 10, that the next octet is 10, that the next octet is 11. The 255 says, I don't care. It can be anything in here. It can be anything between 0 and 255. So anything in that range is acceptable. In this one, we say 172.16.10.0. Okay, we want to be sure it's 172.16.10, but we're only going to allow 3 addresses, or 3 additional addresses. We're going to have the network address, and then we'll have the 1, 2, and 3. So 0 to 3 is what's going to be here. The next network would be 4, which is the one down here, the 30-bit address. So wildcard mask 0.0.0 forward, or whatever it is. If we are in a situation, kind of one of the, I don't really care a whole lot. This one just says, hey, anything that starts with 10 that's on this router, advertise it. So we can do that. And you notice I didn't put a wildcard mask in here. That's only going to work for EIGRP. a network 192.168.11, anything that's on the 192.168.11 network, it's okay. Send it out. So a couple of little shortcuts that you can use in the real world. Don't try this on a cert test, but in the real world, you don't have to get completely involved, I guess, in the wildcard mask if you want to have a whole range of addresses that you're going to advertise on these things. So how you configure it, router EIGRP20, router says that I'm going to configure the routing protocol, the router protocol, EIGRP, router RIP, router OSPF, and what comes after each of those is a little bit different. RIP has nothing. OSPF has what's called a process ID, which we'll look at tomorrow. This one has an autonomous system number. So all of the routers that are in this topology here, in this other autonomous system, the one under a single management, are going to share information as long as they have configured router EIGRP20. They're in the EIGRP20 autonomous system number. If they're in a different autonomous system number, they're not going to talk. They're not going to speak to each other when we do those things. So with that, hopefully we can just go right through these things right now. Cisco still owns it. Several metrics and support multiple paths. Better, more efficient upgrade to RIP, obviously, when we do that, was created to support classless IP addressing. I think I already did that one. EIGRP uses the native IP protocol, and I have never had to do this one. Port 88 is just kind of interesting to know that it uses port 88, native protocol port 88, encapsulated into an IP packet rather than relying on TCP or UDP. RTP, Reliable Transport Protocol, is what it uses. So it has its own layer 4 protocol, which will use these things. RIP was hop count, EIGRP, several metrics, reliability, bandwidth, delay, and load, all of these things. Bandwidth and delay are the only two that had a multiplier. So they're the only two that are going to be used in the calculation of the metric. Advanced Distance Vector Protocol acts more like a link state protocol. RIP sends its updates every 30 seconds. EIGRP maintains a relationship with other routers, uses hello packets. The hello packets, you still there? You still there? OSPF is going to use hello packets too. Are you still there? You still there? As long as the hello packets are active, the router sent them, and the hello packets we saw what was over 15 seconds, I think, was the countdown that we had for those. As long as the neighbor router is up, as long as there's been no changes, then it's not going to do anything. It's another one that's going to be change triggered, which is a characteristic of link state protocols. So it's going to be more efficient that we would have for these things. It doesn't change for a year. EIGRP won't send an update. So it is based up on changes as link state is. Couple of things about it. Cisco proprietary, and again, we still consider it Cisco proprietary. Won't work on non-Cisco devices, OSPF, and I've been to a couple of seminars, I guess, online seminars, and the big wheels there ask, what are you guys using in your networks? Are you using EIGRP, OSPF? And OSPF seems to be the one that's becoming more and more and more popular with everybody, maybe because they're in multi-vendor environments. Multi-vendor environment won't work with EIGRP. It has to be an all Cisco environment. Rapid convergence. Once it has all of the routes, backup routes that we saw in the topology table, they're pre-calculated, they're there, they're called feasible successor. Successor routes are the ones that go into from the topology table, go into the route table. Successor, think successful. Backups are there. Incremental updates. After the initial update, only updates that affect neighbors will be sent. Something happened. Updates. Incremental updates, only things that affect the neighbors, only when changes occur. Load balancing across equal and unequal cost paths. The variance here, and the variance is what percentage of the highest metric does it have to be in order to do that. I said a 2, and I think I actually went the wrong direction, so I didn't really get any unequal cost balancing, but you can modify the variance. We haven't talked about these yet, the autonomous system border routers and the area border routers. This is going to be a function of OSPF, so they're going to be the ones that link the different things together. We can redistribute one autonomous system number into another autonomous system number so that they can share information. But the autonomous system numbers are only going to share routing information, and they share route tables. They're going to only share routing information within their autonomous system. Multicast for updates to 224.0.0.10, multicast. FF02::A for IPv6. Classless, and this uses auto summarization by default, maybe. The older EIGRP routers will use auto summary by default, and if you don't want summarization at the class full boundary, use the no auto summary command. No big deal about that goes along with these things. The layer 4 protocol, it uses a reliable transport protocol, has its own. The packet types, a hello, update, query, reply, and acknowledge. Something that's kind of similar for everything else. Hello, 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 and the hello is still there. Just confirms that the neighbor is still there. Update. Well, query, you use a query, say send me more information, and the query will then get an update, and then a query, needed update, query update is sent out. Okay, well, let me get this. A query, we send a reply update. A query, I need an update. An update is the sending and the reply that goes along with these things, and then the acknowledgement packet, and that's one of you're not going to need to know that process. Hello intervals do not match, and the reason this shows up, if we'd done OSPF first, the timers have to match in OSPF. They don't have to match in EIGRP. It uses the K values that you saw in the show, IP protocols, the K values, K1, K2, K3, K4, K5, K1, and K3, I think it was, had multipliers of 1, which meant those are the only two elements, that's bandwidth and delay, the only two elements that are used for the calculation of the metric. Autonomous system numbers have to match. So K values have to match, autonomous system numbers have to match. Then they really got to be in the same subnet in order to, they got to be able to communicate from one to the other. Basic components of reliable transport protocol, RTP, ordered delivery of these things. Neighbor discovery and recovery mechanisms. I'm going to use the hello messages from the RTP to discover the neighboring EIGRP routers. The whole time determines if a neighbor has failed based on the routers not receiving the hello messages. It's going to be 3 times the hello interval that we will use. Uses the diffusing update algorithm. Responds to changes in the routing topology. Dynamically, automatically adjusts the routing table. That's why we use the dynamic routing protocol. Calculates a loop-free routing topology. And reported distance, again, reported distance has got to be less than the feasible distance. And that kind of makes sense, although you can get into situations that it really doesn't happen. But the reported distance or the advertised distance is the one that comes from the neighbor. What its metric distance is going to be, the terminology for the metric. So it's got to be less than my metric, less than my distance to get there. The bandwidth values, the bandwidth K1, load modifier K2, delay K3 reliability K4, and K5 MTU. And K5 MTU can be a tiebreaker, but again, when you look at the show command, only K1 and K3 had a value other than 0. So the multiplier, and this is a multiplier, not the metric, but it is the multiplier of the metric. A couple of things that happen here, and let's see if I can move this a little bit so that it's in the way. So K1, 1 times the bandwidth. K2, 0 times the bandwidth over 256 minus the load. K3 is 1 times the delay, which is going to be equal to the delay, and the K4 and the K5 is 0 over the reliability plus 0. We're going to go through how it's calculated, and no, don't say, hey, I got to calculate this, or I got to know how it works. You don't got to know how it works. What you got to know is K1, K1 and K3, bandwidth and delay. Bandwidth and delay. 5K values got to match. Bandwidth and delay are the ones that are going to be used for the calculation. The metrics here are not the metrics themselves. So the EIGRP metric, the bandwidth of the slowest link that we go, if we got terabyte, 256K, then it's going to use 256K for the bandwidth for these things. So it's 10 to the 7th over the minimum bandwidth in kilobits per second times 256. This is why you get that crazy big number that goes along with it. The delay is the sum of all the delays in tens of microseconds times 256. Successor route is the best route to the destination, one with the lowest metric cost. A feasible successor goes into the topology table. It's a backup route. If the successor fails, the feasible successor will immediately take over for these things. Feasible distance versus the reported distance here. The advertised distance or the reported distance is, again, the other guy. What its distance is or what its metric is. The advertised distance, or excuse me, the feasible distance is the total path cost. So whatever we calculate here plus what's given to us here is going to be here the feasible distance that we would have for this. So in this one, the routes here, the feasible distance and then the reported distance that would be in each of these. The routes A to D to C, 10 plus 15 plus 5. The 5 here on the outside of it. And this is the one that's confused me for, where does that one come from? Well, we're going to a device or a something back here, so we've got to take this part of it into consideration. So we have here a total thing is going to be a feasible distance of 30 that we would have for it. A to B to C is going to be 25, 35 will be 40, and then A to E to C is going to be 5, 35. The reported distance here would be, we're going to have 30 here, and then the entire thing would be 35. Feasible distance, reported distance less than the feasible distance here to prevent loops. The advertised distance here, 30 or 15. The feasible distance 30. We're okay with that one. So this one's going to be the feasible successor that goes along with these things. Whatever is going to, and what that means is this one's not going to go into the table as a feasible successor. We can have the successor, feasible successor, the route we're going to use, and a backup route. Bunch of different tables that we have in this thing, the EIGRP operations, and this is kind of just a nice summary that goes along. Selects a successor, a primary, and a backup, a feasible successor. So we've got a primary, the successor, and the feasible successor, and injects those into the topology table. The successor is then moved to the routing table. So we have First we have the neighbor table. The neighbor address is the exit interface that goes to the neighbor. From there we get the topology table, the feasible distance and the advertised distance via each neighbor, and from there the best route goes into the routing table, and that's no real magic there. The best route is always going to go into the routing table. What we might have with these things here, what's going to happen, the dual decision tree, and this is just kind of another one of those throw-ins. We have a lost connectivity to the successor. Do we have a feasible successor? Yep. Install it into the routing table, and then we are done with it. They select a new successor and install the feasible successor, if any, in the topology table. If we don't have a feasible successor, place the destination network into active state. Query the neighbor for a new route. Do we have one? If it's yes, then we're going to install it. Otherwise, we're going to remove it. We're going to drop it. And one of the things it says in active state, and one thing that I forgot to show, and probably not a really big deal, in the topology table is show IP EIGRP topology. Over here the code that says P. P is passive up here. A is active. Passive is good. Passive means it's not actively seeking routes. So passive here, P for passive is means that the topology table is stable. It's not actually seeking here. Query for new routes. It places in active state. Go look for new routes that we have. EIGRP, and we've looked at these, so hopefully we'll just click through this. Show IP EIGRP topology table. P for passive. Passive is a good thing, not looking for the route actively. The status of active means that there's instability. It's actually trying to find a new route. It didn't have the backup, so it's something went down, something happened. I need to find a new route that goes along with it. Feasible distance, advertised distance. Feasible distance is the total summation, the complete topology distance or topology metric that gets from the source to the destination. The advertised distance is the distance, the metric to get from the neighbor, from the next hop device to the final destination. We did the show IP route in this thing, and I think in this one we go down. It's probably going to have the arrow here, but let me go in here. That goes into the route table. The feasible distance 217.2416. Which goes into the route table, and again, administrative distance of 90. This is going to be the most trusted, other than BGP, which is an exterior. This is going to be the most trusted interior gateway routing protocol. So all of the other things that we talked about, which one's it going to pick? All other things being equal, it's going to pick EIGRP. EIGRP to OSPF. OSPF keeps all the routes. OSPF keeps the topology, and that's the difference. It doesn't share routes. It shares topology information. So if you lose a route, it's got to do a recalculation from one to the other. So let me finish your note here, which I just saw. Sorry. Well, I'm not that far behind. Keeps all of the topology. EIGRP keeps the successor and the backup. Yeah. EIGRP is so quick. It can quickly create a new route. Yeah, it still has to do the recalculation for the new route, and that's one of the differences. And one of the questions that I saw one time is pick the routers below the no auto summary or something like that. No such thing in OSPF because it's sharing link state, the state of the links information, and it's building a topology table. And from the topology table, the individual routers are connecting the best route. EIGRP is the only one that actually stores the backup from one to the other, and I beat that one to death. But that's why that one happens that way. It's a good question, and I appreciate all the questions, and hopefully I can answer them when we do that. So the metric goes into here, 90. The one that we want to use, and I knew that the arrow would come in. Let me get rid of mine, and we'll get this arrow that goes into these things. This is where you get that crazy number here, 10 to the 7th over the minimum bandwidth in kilobits per second times 256. This one's going to have a minimum bandwidth 56K. You can, if you want to play with this, feel free, but it's not anything that you need to know how to do. It's just a matter of, yeah, this is the way it does. So in this one, we have 10 to the 7th, which is what, 10 million over 56 plus 2200, the total bandwidth times 256, 178,571 plus 2200 times 256. So we get 4,627,000. No, we get 46,277,376 for the metric. It's not in any values. It's a number that's used for comparison. Do any of the others represent a smaller metric? So the smaller metric is the one it's going to use. The neighbor table we looked at. I've only got one more slide after this one, and then there are some questions. I'd like to go ahead and do that, and then we will have a lab. I told you, lab for the rest of the day. A lot of lab time today. Maybe a lot of catch-up time can kind of get a little bit of a dedicated block that other things. We're talking to Will this morning, and yeah, I know other things take place in life to disturb what's going on with these things. But the neighbor table, the address of the neighbors that go along, the interface that's connected, the amount of time left before the neighbor is down, and that's the one that's going to get reset. The amount of time since the adjacency was established. How long have we been talking to this particular device? Adjacency requirements, active hello packets, autonomous system numbers, and the K values have to match. They used to, and they don't have these kind of questions anymore. Have ones that they call hotspots, to where they said this happened, and the one was that a junior network administrator just went in and installed a new EIGRP router, and it ain't talking. What's the problem? You have to go in and use the show commands and find out what is the issue. And the only real issue you could have is autonomous system numbers don't match, not sharing information. K values don't match, and then it could be the answer, or in some of the cases in the labs, you'd have to go and do a configuration change to these things. EIGRP for IPv6 allows IPv6 to be configured using the global IPv6 address. No network statement, so the networks aren't going to be advertised. You activate it on the interface, and it shares the information with the adjacencies on those interfaces. And when we did the show command on the one that had both IPv4 and IPv6, you configure, and it's just a matter of, it was what, IPv6 EIGRP 20, whatever the autonomous system, 10 for that one, I think, for that particular one. Instance will require a router ID. We have to go in and configure the router ID manually, and that's just a matter of having it in these things. You got to have a router ID. The router ID, the name of the router, it's what is going to be used. It's the address or that's going to be used to share the information. And this is one that probably a good idea to just go ahead and put a virtual interface in, or a loopback interface in, so that you can do this. This is an odd protocol in that it starts up just like the interface is doing the shutdown mode. It's the only one that you have to give the no shutdown mode in order to start it up. You can use the passive interface command. Passive interface, it's not going to establish adjacencies in that particular one. The distribute list, prefix list, and the route map, something that is beyond the IPv6, maybe uses uses a route map. Route maps, if you go onto CCNP, you'll construct route maps. So in order to configure EIGRP for IPv6 unicast routing, anytime we do IPv6 anything, IPv6 unicast routing, it's not the default IPv4 is. The routing protocol IPv6 router EIGRP on the interface, and then the autonomous system number. And then in the the IPv6 EIGRP configuration, router ID has to be specified, and then you use the no shutdown command. So yeah, loopback is always a good thing to use for these things, and then the EIGRP autonomous system numbers that are there. I think there are like 4 questions, and then we can get into labs, and I know that they don't always go smoothly. Hopefully a little bit of block today and a little bit of block tomorrow will help out in doing those things. But what is a dynamic routing protocol? Manually configured routing entries, especially useful in small networks, an administrative nightmare in large, constantly changing networks, a network where the routing protocol adjusts paths automatically based on the topology and or traffic. RIP, OSPF, EIGRP, IS to IS, and BGP are routing protocols used mainly as interior and exterior gateway protocols, HSRP, OSPF, and so on. I got a D and a G. I'm not real wild about G because of HSRP, which we haven't done yet. Hot standby routing protocol. Yeah, D, E, and F, I think, probably look pretty good for this one. What is the wildcard mask equivalent of 255, 255, 255, 192? Well, you know it's going to be 0, subtract from 255, 0.0.0. something. And when we subtract 192 from this, we're going to get B here. We're going to get C here. The 8 would be for what? 248. If it was 248, it would be 8. 255 minus 192. And I know I take more time than most of you want me to, but we'll go to 255. Subtract all 255. That's going to be 0.0.0. With 255 here, subtracted from that, 5 take away 2 is 3. 6, so it's going to be the 63 here would be a wildcard mask. We're going to use wildcard masks for routing protocols, and we'll also use wildcard masks for access control lists. Yeah, my math is usually off. You guys have to watch me when I start doing those things. Start doing the math that goes along with these things. 3 distinct disadvantages of a link state routing protocol. We did that. I'm just going to say, hey, it's going to be memory requirements, router CPU load, bandwidth utilization. We really haven't talked about link state protocols. We talked about the generalities of link state. They're going to share all of that topology information initially. After that, they kind of go quiet. They don't do anything unless there's a change. Are correctly associated with the type listed. OSPF is a link state, EIGRP link state and distance vector, advanced distance vector. RIP distance vector, RIP-v2 distance vector, or all of the above. And that one's going to be all of the above. So we do have